Okay, so there is a particular application of the law of large numbers that is of great, that provides great insight on what is the nature of typical sequences. Okay, so let me take again a sequence of random variables which are independent and identically distributed. Let me take the situation where the xi take value in a finite set. Okay, so these are random variables that take up, they are discrete and take up a finite number of possible values. Okay, so then let's consider a sequence of n elements. Let me call it x with a vector for simplicity. So this is the sequence of the first n elements. And let us consider what is the probability of this sequence. So the probability of this sequence clearly, because the random variables are all independent and identically distributed, it's just the product of the probabilities. Okay. Now, if this is true, then if we take the logarithm of the probability of a random sequence and we divide it by 1 over n. So let me specify that this is we are considering a random sequence. Then this is 1 over n. The log of this, the log of the product is just a sum. And now you see that we are exactly in the condition of the law of large numbers, in the sense that if we take very, very long sequences, then as n goes to infinity, this will converge almost surely to the expected value of the log of p of x. Okay, what is this? Well, this is just minus the sum over all values of x, p of x, log p of x. So this is plus. So this is object as a name, and it's called it's minus the entropy. This is the definition of the random variable x. Okay, where the entropy of the random variable x, let me write it here, is minus the sum over all values of x, p of x, log p of x. So what we learned is essentially if n is large enough, then the probability of a random sequence will be essentially almost surely of the order of e to the minus n times the entropy of the random variable x. Okay, so this is quite remarkable, because it tells you that if you draw a random sequence, its probability will be almost equal, almost surely equal to, very close to this value. So this means that all sequences have, all random sequences with very high probability. If you take a random sequence, it will have this, the same probability, which is this. And this is what is called the asymptotic equipartition property. It's the property that every sequence that we draw at random, IAD from a distribution, with very high probability, has exactly the same probability. Okay? So this has a number of consequences that that are very interesting. And so in order to define these things, to be more precise, let me define epsilon typical sequences. So we define the set of epsilon typical sequences, that is called the one define it in this way, as the set of sequences such that 1 over n times the log of the probability of the sequence plus h of x plus the entropy is less than epsilon. Okay? So these are the sequences for which the probability is very close to e to the minus n times h. Okay? So what we have just shown, so the law of large numbers tells you that the probability of x is essentially equal to e to the minus n times the entropy of x. This is for all epsilon typical sequences. So this is just a definition, so it's just a consequence of this definition. So this definition implies that all sequences in this set have a probability which is equal to this. But the law of large numbers tells us that the probability that we get a sequence in this set, or the probability of an of x, so the probability that a sequence, a random sequence, belongs to this set here, is essentially equal to 1. And because we almost surely, actually, so you can say that this is larger than something like 1 minus epsilon. Okay, it's very close to 1, asymptotically close to 1. And as a consequence of these two things, the number of epsilon typical sequences is essentially of the order of e to the n times the entropy. Okay, so so why is this? Because essentially it's a consequence of the previous two results. And so if you want to compute what is the probability, so we said that the probability of an of epsilon, this is essentially equal to 1, but this is the sum over all sequences in an epsilon of the probability of the sequence x. But all the sequences in this set have the same probability, which is essentially e to the minus n times h of x. And what remains is the sum over all the sequences in this set of 1, which is just the number of sequences in this set. So you see that this equality tells you that essentially the number of sequences in this set must be e to the n times the entropy. Okay, so this is quite interesting because it tells you that when you draw at random a sequence from a probability distribution, the type of sequences that you draw are very specific, with very high probability, have very specific properties. So one is that they all have the same probability, and the other one is that they are very few in number. So if you consider the set of all sequences, so the set of all sequences is essentially so the size of the set of all sequences is essentially the size of the set key to the power n. Okay, so this is, if this is the set of all sequences, then the set of epsilon typical sequences is a very small fraction of this. Okay, because typically h of x, so if you see, I mean, the fraction of epsilon typical sequences is given by this, and it will be e to the minus n times log of key minus the entropy. And you can easily see that so the entropy is always less or equal than the log of key, and because of this, this is always negative. Okay, so if I take a sequence at random in the set of all possible sequences, the probability that I find an epsilon typical sequence will be exponentially small. Okay, and yeah, so these epsilon typical sequences are very, very few compared to the all possible sequences. Okay, so the other thing that I want to discuss is other characteristic properties of typical sequences. Okay, so now if you take a sequence of n random variables, then you can define the number of points in this sequence that are equal to x. So that essentially you take the set of all indices such that xi is equal to x, and you count how many variables in the sequence are equal to x. Of course, you should have the sum over x and all possible values of x, of m of x, must be equal to n, because n is the total number of points in your sequence. And but now I want to understand what happens in the limit when the length of the sequence goes to infinity. And typically, well, I also expect the number of these M of x will also go to infinity. Okay. Now, what is the probability of a typical sequence? So, one aspect is that the probability of a typical sequence can be written in this way. And but this can also be written as a probability of x as a product over x to p of x to the m of x. Okay. By the way, notice that this m of x depends on the sequence, so it depends on the sequence x, but I'm not going to have a lighter notation. I'm going to drop this dependence. Okay. You see, for a random sequence, the probability only depends on the sample through this quantity. So that the count, how many points in the sample are equal to x. Okay. And the second thing is that we can think of, so imagine that you have a certain profile of m, so this is the set of m, the vector of m of x for all the x in Q. Then want to ask, what is the probability that we, if we take a random sequence, we get exactly a particular value of these counts m of x. Okay. Well, for any sequence that have this m, the probability is the same and is given by this. And then how many sequences are there? Well, it's just a multinomial factor. So this is the number of sequences that have the same counts, the same m of x, and the probability of each of them is just the product over x of px times m of x. Okay. This is just the multinomial distribution. Okay. Now you can use Stirling formula for n factorial and for m of x. And I leave it to you as an exercise. And what you can see is that you can approximate this by the exponential of minus the sum over x of m of x times log of m of x divided by n times p of x. Okay? Very good. So now what you can see is that this you can also write it as minus n times m of x divided by n. And it's easy to show that sum over x of m of x divided by n times log of m of x divided by n times p of x. This must be positive. Okay. So how do we do this? Well, let me invert this ratio here and take a minus sign. Okay, so minus x m of x divided by n times log of n p of x divided by m of x. So this is, I just rewrote this thing. And now I use the property that the log of x is less or equal to x minus 1. So you can check that this is actually true in different ways. But if you apply this equation here with a minus sign, means that this is larger or equal to minus the sum over x of m of x divided by n times x is n times p of x divided by m of x minus 1. Okay, so when I take the first term, so the n and the m of x cancel with this, I have just the sum over x of p of x that gives me 1. Okay, so this is minus 1. And when I take the second term, this is just the sum over x of m of x divided by n. The sum over x of m of x is equal to n. So this is plus 1. So this is equal to 0. So you see that this exponent here, this constant here, is always positive. But you see clearly that this is equal to 0 when m of x is equal to p of x. So, so the only the probability that I get say an histogram, a count, so the number of points in my sample which are equal to x is essentially the histogram, if you want, when you do when you count the number of so the probability that you get an histogram m of x that is different from n times p of x. So the probability of this thing is essentially exponentially small in n. So it's essentially going to 0 as n goes to infinity. So this tells you with probability 1, your sample will be very special in the sense that with probability 1 you expect that the number of points that are equal to x, the fraction of points that are equal to x in your sample approach the probability of x. Okay, so this is a characterization of what is a typical sample, what you expect to occur typically when you draw random numbers from independently from a probability distribution.